Check this out. We've got something really fun today. This is so amazing, math. Oh man, again? 1.6, limits of infinite sequences, convergence, and we're going to put in here as well, horizontal asymptotes. A sequence is a set of elements, and we are going to use numbers, could be elements other than numbers though, that have a specific order. For example, 2, 4, 6, 8. 3 dots means it goes on forever, and that's what we're going to be interested in this course. This will be the first term, and we'll call it T1. Second term is T2, and so on. This would be the nth term. And for these sequences, there's always a formula or algorithm for finding the terms in the sequence. Arithmetic sequence. That would be a sequence where the difference between the terms is a constant number. This example could be described as Tn equals 2n minus 1. Now there is a formula that we learned in grade 11, and it was Tn is equal to T1 plus n minus 1 common differences. So in this case, T1 is just 1, and the common difference you can see is we're adding 2 each time, so the common difference is 2. And then if we distribute in the 2 here, we get 1 plus 2n minus 2, and if we collect up like terms, this is what we get. Now really, if you look at this closely, this is a linear equation in slope y-intercept form, and you can see the slope is equal to the common difference. And the y-intercept would be the t0 term if such a term existed. Now it doesn't. Very important point. The sequences start at t1. There is no such thing as a t0. But if there was, see if you could back up one more step, that would be -1. Let's try this one. The common difference looks like we're subtracting 3 each time, so -3n. And if I could just go backwards one step, we would have been at 6. So it's +6. Now we could do it using this same equation. So Tn is equal to term 1, so 3 plus n minus 1 common differences, and that'd be -3. And we could sort this out, 3 plus or minus 3n plus 3, and collect it up, and it would look just like this. Now what is the last term in this sequence? Well, there is no last term because these 3 dots say that it goes on forever. But if we take the limit as n approaches infinity, this n right here, we might find where this sequence gets closer and closer to. Our first example here, let's try it. The limit as n approaches infinity of 2n minus 1. Now if we put infinity in here, we've got 2 times infinity, which is still infinity, and infinity minus 1 is still infinity, which means that this limit does not exist. Let's try this one. Put 6 minus 3 times infinity. Now 3 times infinity is still infinity, so 6 minus infinity. Well, the 6 really doesn't matter in the long run when we have a minus infinity, so this heads off to negative infinity, which means that it also doesn't exist. So these sequences both diverge, which means they approach positive or negative infinity. Can you think of an infinite arithmetic sequence that doesn't diverge? So maybe you thought of something like Tn equals 1. So anything where the common difference is equal to 0. And then the sequence stays the same the whole time. Those are kind of boring though. Geometric sequences is where each term is multiplied by the same number to get the next term. We had a formula for this from grade 11. It would be Tn is equal to T1 times the common ratio n minus 1 times. And the common ratio is r here, and it's the number that we're multiplying by each time. In this example, our first term is 4, so that's why there's 4 here, and we're multiplying by 2 each time, so that's why there's a 2. Now there is something we can do with this algebraically, so let's see if we can simplify this exponent. We'll leave the 4 for a minute, and the 2 to the n, and let's get rid of this minus 1 by writing 2 to the power of 1 in the denominator. Now we can see, really, we could do 4 divided by 2 to simplify this further, and that would be 2 times 2 to the n. And that's interesting. There's a lot of things I could have done, like bring the 4 in here for a second, but I wanted to get to this point here because this looks like an exponential function, and exponential function, and that is the y-intercept of the exponential function. Now we could bring this back in or bring the 4 in the first place, and we could rewrite this as 2 to the power of n plus 1, but this has a lot more meaning. How could we express this sequence in general terms? So we could start off with this equation here. So I'll do that this time. Tn is equal to T1 times the common difference, and that looks like it's a half each time. So half n minus 1 times. Now I'm going to simplify this. I don't like the minus 1 in the exponent, so let's get that out of there. So we've got 1/2 to the power of n and 1/2 to the power of negative 1. Instead of putting it in the denominator, I could just separate it like this. Now if I got negative 1, that's going to flip this around, and so it's really 10 times 2. So that would be 20 times 1/2 to the power of n. So if we were going to consider this as an exponential function, that would be the y-intercept. And you notice that if we just back up a step, our t0 would be 20, if such a term exists. But it doesn't. There is no such thing as a t0. It starts with t1. I'm only mentioning t0 because it's easy to connect this y-intercept with the concept of t0. And if you can do that, it's much easier to jump to this simplified form of the equation right away without going through the steps or maybe even remembering this formula. Let's find the limit of these geometric sequences as n approaches infinity. So the first one here looks like it has a term 1 of 4 and a common ratio of 2. But if we let n approach infinity, we're going to have 2 to the power of infinity minus 1. Now infinity minus 1 is infinity. And 2 to the power of infinity is also infinity. And 4 times infinity is still infinity. So this thing is going to head off to infinity, which means that the limit does not exist. Let's look at the next one. The limit is n approaches infinity of 8 over 7 to the power of n. We can break this apart, and that might help you visualize what's going on here. So we have 8 to the power of n, and we have 7 to the power of n. Now, if you think of these two independently, we've got 8 to the power of n, or 8 to the power of infinity. Well, that's going to be infinity. And we've got 7 to the power of infinity. Well, that's also going to be infinity. But slow down. We've got this 8 is larger than 7. So in this race to infinity, as it were, 8 is actually going to get ahead of 7. And it's going to eventually be infinitely farther ahead than 7. So this one wins the race, so to say, to infinity. And so overall, we would say then, this heads off to infinity. which means that the limit does not exist. Let's look at this one. Term 1 is 10, our common ratio is 1/2. So 10 isn't really doing much here, and let's rewrite this. Maybe it will be a bit more clear, but 10 is in the numerator. If we give 1 an exponent, it's not going to change it, so I'm just going to forget about that. And the 2 has an exponent of n minus 1. So I've just rewrote this so that I can see where this is going. Now the numerator is staying right where it is. It's the denominator that's increasing. So this is a case of we have 10 cookies, and we're going to share it with 2 to the power of infinity. Well, that is infinity. So if you have 10 cookies and you're going to share it with an infinite amount of people, well, essentially you are going to get 0 parts of that cookie. So this sequence actually converges, which means that as we approach infinity, the sequence gets closer and closer to a specific value. It doesn't actually have to equal 0 ever because there is a 10 here in the numerator, but it's a limit, remember, and the limit just cares about where is it getting closer and closer. So it's getting closer and closer to 0. Check out this other sequence. Now, let's determine if it's arithmetic or geometric. So arithmetic. And if it's arithmetic, then there should be a common difference. So 2/3 minus 1/2 should equal 3/4 minus 2/3. Let's see if that is the case. So it looks like we need a common denominator of 6. So 4/6 minus 3/6 is 1/6. And common denominator 12, so 9/12 minus 8/12 is 1/12. So we do not have a common difference, so it's not arithmetic. Okay, let's check out geometric then. And if it's geometric, then it should have a common ratio. So let's say 2/3 divided by 1/2 should be the same ratio as 3/4 divided by 2/3. Now, if you want, you can pause the video, see what you can figure out here, find the general term, and then, of course, play the video once you have your answer. That would always be a good practice. Okay, let's run through this, assuming you're done with that. So I would flip this 2/3 times the reciprocal, and that would be 4/3. And 3/4 times the reciprocal, and that would be 9/8. Okay, well that doesn't work either. So this is not geometric. Let's see if we can find the general term then. We would want Tn to equal. Now, something we notice is that this is term 1 and the numerator is 1, term 2 and the numerator is 2, and so on. So actually we could just say the numerator should be n, and the denominator is always 1 ahead, so the denominator could be n plus 1. Let's see if we can find the limit as n approaches infinity for this sequence. Now I usually just think my way through this. So if we had n here, that would be infinity. And I'll just use quotations. If you ever write infinity, you can't actually have that in a calculation, so that's why I'm using these quotations here. And in the denominator, infinity plus 1. Well, the farther and farther we go, the less and less that this plus 1 matters. So whereas this one is 0.5 and 0.666, 0.75, and so on, we're just getting closer and closer together. So really, this limit would equal 1. Now, some people don't like thinking their way through this, and they want some math to do. So let's also see what we can do with this. This is division. So let's say we have n, and we divide it by n plus 1. Now, what would I need here then? Well, I just need a 1 actually. So 1 times n plus 1. And we always subtract here. So n minus n is 0, and 0 minus 1 is negative 1. So we can rewrite n over n plus 1 as 1, the one that divided off evenly, and then our remainder is minus 1 over n plus 1. And then when we write the limit as n approaches infinity of all of this, 1 minus 1 over n plus 1, see that this is unaffected by n, so that will remain 1. And this term here is 1 over infinity, which is, as we saw in the last example, goes to 0 or approaches 0. So 1 minus approaching 0 is just 1. Does this sequence converge or diverge? So because it approaches a value here, we would say that this converges. What about the Fibonacci sequence? How would you write the general term? So we've got term 1 equals 1, and term 2 equals 1, and term 3 equals 2. We're actually going to use that in our general term. So Tn is equal to the previous term plus the term before that. And in this general term, I need to say that, let's see, n needs to be greater than or equal to 3, because if we had something less than that, then we'd have negative terms here, which wouldn't do at all. And n is also a natural number. Does this sequence converge or diverge? So we would say it diverges because it doesn't approach a single value. Now consider this sequence. It doesn't appear to be arithmetic or geometric, but you can investigate that just like we did in previous examples. Let's find the limit as n approaches infinity of this sequence, and the general term would be 1 over n. So if n approached infinity, then we would have something like 1 over infinity, and we could think our way through this one. If you had one cookie and had to share it with infinitely many people, then how much of that cookie are you going to get? Well, soon it will be so small that we couldn't measure it, and so this limit gets closer and closer to 0. Now I know there's a 1 here in the numerator, but a limit means what does this get closer and closer to? All right, what happens if it's 1 over n cubed? The cubed really has nothing to do with the limit. The limit is changing n's value, and so this cubed can just wait on the sidelines until the limit is done. So I could actually take that cubed out of the limit and apply it after the limit is done here as follows. And now this is actually what we just did over here. And so this is 0 cubed. And so really you see the cubed can't do anything with that. And so it's just 0. This is a very important result, and we'll use this to simplify other rational expressions. So in general, if we ever have this, the limit is n approaching infinity of 1 over n to any exponent greater than 0, it's going to equal 0. Now let's find the limit of this rational expression as x approaches infinity. Now there's a whole lot going on here, but here's our strategy. We're going to simplify by dividing every term by the highest powered x, and then we're going to take the limit of the individual terms. So let's see how that will work. The limit as x approaches infinity. Now the highest powered x is x squared, so we're going to divide everything by x squared. And in the denominator, and now let's simplify each one of these terms. So the limit as x approaches infinity. This one will simplify to 1, 3 over x, 5 over x squared. It's 2, 1 over x, and 1 minus x squared. Now we'll bring the limit in. So we're going to take the limit of each individual term, see where they're going, and then add the results together and divide this stuff here. So the limit as x approaches infinity of 1 minus, and the 3 is a constant, so I don't need it in there as well. I'm going to take it out, so minus 3 times the limit as x approaches infinity of what's 1 over x is left in there, plus 5 is also not affected by this limit, so I can just set it aside and let the limit do its thing here, and then I'll multiply by 5 after. So this would be 1 over x squared. Ooh. In the denominator, I've got the limit as x approaches infinity of 2, plus the limit as x approaches infinity of 1 over x, and finally the limit as x approaches infinity of 1 over x squared. Now, given the result that we found last time, this limit here is going to go to 0. This limit here is also going to 0. Same with this one, same with this one. And you can see why we divided every term by the highest power x, because the only thing that's left are these ones. Now the limit as x approaches infinity, this has nothing to do with x, so could have taken it out here, so it's 1 over, same with this one, 2. And this is actually the horizontal asymptote, at least y equals 1 over 2 would be the horizontal asymptote. Now remember, this graph never actually, if it was a graph, never actually equals 1/2. But remember, that's not what a limit is. A limit is saying as this variable approaches this, what does this approach? So as we go off farther and farther towards infinity, this graph gets closer and closer to 1/2. Never makes it, but that's what it's getting closer and closer to. Now in 30-1, we learned this trick to help us find our horizontal asymptotes very quickly. So we just looked at the coefficients of the highest powered x. We didn't go through all of that stuff as we did on the last slide there. We just looked at these and then we said everything else is going to go to 0, just these will be hanging on here. So 4 over 2, which is just 2. Let's do the next one here. We've got 16 as a coefficient of the highest powered x, and we don't have any x cubed in the denominator, so essentially that would be 0 x cubes down here. So this would be 16 over 0, and I put it in quotations because I can't actually have that, but I can see where that's going to go. If this one got closer and closer to 0, and this one was at 16 here, this would head towards infinity, which means that this does not exist, this limit. So no horizontal asymptote. Remember, if we divide by something closer and closer to 0, it gets larger and larger. And finally, this one here, this one we have the reverse. We have 0x cubed in the numerator, and we've got 5 in the denominator. So this one will be 0 over 5, no problems here, and this just equals 0. Find each limit. Now these are pretty interesting, so pause the video, try them out, and restart once you've found the answer. Now the first one here, we've got a -1, and x is going to infinity, but we know that if x is an even number here, then that will actually get rid of our negative. But if x is odd, then we'll still have a negative here. So is infinity odd or even? This one doesn't approach a single value. It's just oscillating between -1 and 1, so it's not getting closer and closer to a single value. So all we can say for this one is that the limit does not exist. What about this one? We've got 2 over 3 to the power of x. Now, just like before, it'd be 2 to the power of x over 3 to the power of x. 2 is smaller than 3, so in the race to infinity, 3 to the power of x would be infinitely further ahead than 2 to the power of x. So the denominator is infinitely larger than the numerator. So that would mean this one is 0. That would be the same case for this 4 to the power of x and 5 to the power of x. Well, 4 to the power of x is going to be less than 5 to the power of x, and so 5 to the power of x is going to be infinitely larger than this numerator here. And so again, this is equal to 0. Now this is an important rule. If the absolute value of r, this right here, is less than 1, another way to think about this is if r is in between -1 and 1, then the limit of r to the power of x as x approaches infinity is going to be 0. And finally, what are the horizontal asymptotes for the following functions? So g of x is equal to 2 over x, so the horizontal asymptote here would be y is equal to 0. Let's try the next one. The horizontal asymptote, let's put HA, I guess, would be, here we see this is a power of 4, and this is a power of 4, and looks like that's our highest one. So 6 over 9, or y is equal to 2/3. And the last one, our horizontal asymptote here, would be, we have an x to the power of 2, and we do not have that in the denominator, so this horizontal asymptote does not exist. After this lesson, you should be able to find the limits of infinite sequences, determine if a sequence converges or diverges, and also as a side note, find horizontal asymptotes for rational functions. Here's some questions from the textbook. Give them a try, see if you know what you're doing.